Okay, so we will continue with this soft and hard magnetic materials. So I'll just make a like a flow chart so that you can remember it. So let's say we have, this is our magnetic material. So one is, we call it as a soft, so magnetically soft, and then we have other side, we have a hard magnetic material. So soft means it has a low coercivity, okay? And here we have a high coercivity. So that is not the only thing, okay? So is the spring proper? I can bring it a bit closer. Okay. So you can you have high coercivity. So not only that. So in this case, for soft magnetic material, you also have permeability is also high. Okay. And so this is another property of the soft ferromagnetic materials. And when you look at the material, so we discussed that when you use this soft magnetic material in transformers, so you can use it in for AC field applications. So you can use it in transformer, motors, generators. Okay. So these high coercive hard magnetic materials are used as permanent magnets, or even magnetic recording mediums, and so on. So these are the applications. So how do we achieve low coercivity or change the coercivity? So that is normally, I mean, there are many parameters which there is not enough time to discuss all the contribution to this. The major contribution is the magnetic anisotropy. This is a magnetic anisotropy. So that means if you can reduce the magnetic anisotropy, okay, so if it is small, so you get low coercivity. If it is large, you will get high coercivity. So this way you can choose or prepare your material in such a way. So of course, then I am not discussing about how you can control or manipulate magnetic anisotropy in the material. So that also one can do by some way of sample preparation. Okay, so that is where the material engineering comes in. Okay, so if you can prepare alloys with special elements, special materials, with special crystal structure, so then you can control this magnetic anisotropy, and you can use it as a soft ferromagnetic material or as a hard ferromagnetic material. So in the soft case, so what is the contribution of? So basically, when we use it in any AC field, so you have a ferromagnetic material, okay, a soft magnetic material. So let's say this is a soft magnetic material, and you are applying So this is, let's say, domain 1. So now the question is, now if you are applying a magnetic field or an AC current, so what you are doing? What you are doing is basically you are driving the hysteresis, right? So you are driving the hysteresis from a positive saturation to a negative saturation. So that means using this, during this process, you lose energy. So there is a loss during this process. So when you use it in any AC field application, so there is a loss of energy. Yes.
So will you please adjust your screen? It is not visible.
Not visible.
The board is blurred very much.
Okay. So if I bring it closer, is it better?
Yes, a little bit better.
A little bit. Okay,
Yes,
I will
sir.
write
Now
big.
it's visible. Now it's visible.
Yeah, I use a big font. Okay. So when we talk about this when we are driving the hysteresis, so that means we have. So let's say we have this. So we are going to a saturation, positive and a negative saturation. So basically, what we are doing is, if we have such a simple configuration, magnetic configuration. So magnetization along this and pointing like this. So we have a domain 1 here. Basically, what we are doing is moving the domain wall, right? So moving it towards right or left. So this is how we can achieve saturation. So the energy loss depends. So one, we discussed that we need a smaller. So we use a small hysteresis loop. Okay. Or what we can do is we can reduce. So there are other losses. This loss due to eddy current. So what are contributing to the eddy current? So one is basically just like, since you have a change, let's say. So when you are applying a current I, some current I to the magnetic material, so it is going to oppose. So it will induce EMF, which is going to oppose this magnetic the current, and it will produce an eddy current in the opposite direction, which is given by the IEC. And this is basically will be a loss of the magnetic. This is a loss basically, power loss due to this eddy current. So this is one way of looking at eddy current. But if you look at microscopically, what is the reason for this eddy current? So the eddy current is actually produced very close to the domain walls. So it is not produced in the domains. So of course, so the eddy current depends on the domain size. So how big or the small the domain is, and also on the, so I can write it down in a better way. So if I say this eddy current will be proportional to size of the domain. So this is size of the domain. and also it will be proportional to n domain wall. So number of domain walls, or it is actually inversely proportional to this. Okay. So if I increase the number of domain walls, so I will decrease the eddy current, and if I increase the size of the domain, so if I have bigger size domains, so I will increase the eddy current. And this eddy current, which is let's say if you look at a magnetic material, eddy current will be, you can write is the domain wall. Domain wall. So it's a vector sum, or let's say you have many domain walls. Okay, so not only one. So if I take a normal ferromagnetic material of any arbitrary state, so I have many domains. So there are not one domain, not one domain wall, but more than one domain wall. And so each domain wall is going to contribute to your eddy current. Okay, and this eddy current, total eddy current, will be a vector sum of so I can write this as a vector sum. So this is a domain wall, eddy current due to the jth. So I say this is j equal to, let's say, 1, 2, 3 in this case. So if I have 3 domain walls, so the eddy current will be the total eddy current in the sample will be a sum of the eddy current due to these 3 domain walls. So basically, you can have more than one domain wall, and this will go from j equal to 1 to n, and you can sum over that. So this is a theoretical understanding, but it is not easy to model this thing. So there are simple models, basically models where we assume 180-degree domain wall or 90-degree domain wall and so on. So you cannot model for a very generic sample. Okay. So that is about the soft magnetic material. Yeah, so what are the different soft magnetic materials that exist, that are used in the industry? So one is, of course, this iron carbon. This is an alloy. Okay. So this is an iron carbon alloy, which is also known as electrical steel. Okay, and then there is also iron silicon. So this is also a kind of steel. Okay, so this is also a soft magnetic material. Then there is iron. So we can take iron and cobalt. So normally it is used in 50-50 combination. So that is another soft magnetic material. You can also take iron and nickel. So here in this case, this alloy, so these are all what we are writing down as alloys. Okay. So here you can have different combination of nickel. So the most used is I think 79% nickel or 80% nickel. So this is mostly used. So the rest is iron, but also people use 50% nickel as well. Okay, so this is also used. So it depends on the industry, like what they make. So and remember, just a moment. So remember, these are like the major atoms in the alloy. So there can be many other impurities that are added by companies which they do not disclose always, but these are the major components. Okay, so you can add, for example, in this one, sometimes people add copper. So it is. So one thing is you are looking at the magnetic properties. Okay, so for soft magnetic material, what we need is a low cohesivity and high permeability. So that is the first thing. But then there is also, you have to look at the mechanical properties, the stress. So how much stress it gets. Okay, so if you have more stress or more defects, so that is going to affect your magnetic properties as well. So um, these little things are not, let's say, maybe can be neglected in the beginning, but when you are making a real product, so you cannot neglect the defects and impurities. So that's why you have to add some other impurities, like as a deliberately. Okay, so without, I mean, it is not unnecessary. It is deliberate. You want to add these impurities so that you can improve some other properties. Okay. Yeah, and so all these are some kind of like metallic behaviors. Okay, so they show some kind of metallic behavior. So there is another kind. So as I said, how can you decrease or reduce the eddy current? So eddy current you can reduce by increasing the resistivity. So most of these materials which I wrote, so they have some kind of they are metallic, so they are better conductors, right? So the resistivity is low. So that's why you will always have an eddy current loss due to that. But if we can make a material where rho, it's a very high resistivity, so then you can practically forget about the eddy current loss. And such kind of materials, they do exist. So these are like known as magnetic insulators. Okay, or they are also called ceramics. So the most common ceramics that are used are known as ferrites and garnets. So these are the two kinds of soft magnetic materials which are actually insulators, and practically there will be no eddy current in such kind of materials. But of course, if you compare it, like, so why don't we use only ferrites? So the reason is like for low frequencies. So when we are working with 50 hertz or 60 hertz, okay, so that is what commonly we are working with. So in that case, so electrical steel, so which I wrote in the beginning, this iron carbon or iron silicon compounds, they are cheaper as well as work relatively with better efficiency. I mean, of course, these will have better efficiency than those materials, but still the price will be higher. Okay, so that's why. So we use iron, this steel material for normal application. But if you want to go to really high frequency application, so like if you want to go to 1 megahertz, so like some communication, or even gigahertz range. If you want to use materials in this range, so you have to use ferrites. Okay, so these are the material choice for high frequency application. So if you want to like go into a microwave regime in the gigahertz frequency, So there you have to use ferrites. So basically, the ferrites are, so one is nickel, zinc with, so this is a kind of ferrite. So definitely this is called a nickel zinc ferrite. And then there is another one is a manganese zinc. Manganese zinc ferrite. Okay, so it is also called a manganese zinc ferrite. So these are the widely used ferrite, soft ferrites that are used in communication devices. Okay. Yeah, so this is about the soft ferromagnetic material. So when we talk about a hard ferromagnetic material, so we need a higher coercivity. Since we have 5 minutes left, so we'll start with the hard ferrites tomorrow. But I just want to give you some kind of idea how one can. So in physics, we want to model things, right? So I mean, even you guys would like to model things and simplify things so that you can understand what is the underlying properties, how you can control and so on. So in the beginning I said, so if I take a ferromagnetic material, so when I'm applying a field, okay, so what is happening? So basically, when I am trying to saturate it, that means I am driving the hysteresis. Okay, so I am increasing the field. So how this happens? So there are two ways. So one is domain one motion, and second is rotation of magnetization. So if you look at the hysteresis, so it is always something like this, what we plot, okay? So up to this field, so you could say that this is a domain one motion. And from here to here, you would say a rotation of the magnetization. Okay, so in the beginning, what happens? You move the domain walls. So let's say, so this is how my domain looks like. So when I apply magnetic field X in this direction, let's say this slide, yeah, something like this. So what is going to happen? That magnetization should be all like this. Okay. So I move the domain walls in such a way that I'll create something like this. So some domain walls will go out or will be gone, so new domain walls will form. And then finally, when I reach the saturation, so when I go to saturation, so whatever the magnetization is here, they have to rotate to the field direction. Okay, and then everything should be pointing like this. So this is the two regimes how this hysteresis happens. Okay,